All right, let's dive right into this explainer, because I'm going to show you how to solve a high-value Cambridge exam question faster than most students even read it. We are totally bypassing the fluff today and going straight for the high-yield strategies you need for IGCSE Computer Science 0478. So consider this typical exam question. Explain how a computer stores data in its memory. I mean, it looks pretty simple, right? But you'd be amazed how many students see this and instantly lose marks by falling for a massive psychological trap. They panic, write down the very first thing that pops into their heads, and completely ignore the actual physical reality of the hardware. The harsh reality here is that ordinary revision fails you when you imagine computers have tiny numbers physically sitting inside them, like some sort of electronic alphabet soup. If you write down that it stores ones and zeros inside the memory chips, you're getting exactly 0 marks. Because think about it, if you literally crack open a CPU, you are not going to find a sea of microscopic ones and zeros floating around in there.
Section 1. The core concept, binary and data. Let's get into it. Okay, the absolutely crucial point to remember is that a computer is, at the end of the day, just an electronic machine processing data. And to do that, it relies entirely on physical components that have just 2 states. Think of a standard light switch. It's either on or it's off. There's no in-between. That is the true definition of binary, anything that can exist in 2 different states, and only 2. It's actually not about math first. It's entirely about physics and electricity.
The binary number system of 1 and 0? Well, that's simply our human shorthand for mapping out those real electrical signals. We use numbers just because it's a heck of a lot easier to write down digits on an exam paper than trying to draw millions of microscopic electrical switches.
Every single fact, figure, image, or sound you interact with has to be converted into these bits, binary digits, and then we group those into 8s to form a byte. This is completely different from our normal base 10 denary system, which obviously has 10 states, or even the hexadecimal system, which operates on base 16. Inside the machine itself, it is strictly 100% base 2.
To truly appreciate this shift, you kind of have to look at the history. Our normal 10-state denary system actually comes from ancient Arabic mathematicians like Al-Khwarizmi. But it wasn't until Gottfried Leibniz back in 1679 and then Ada Lovelace much later in the 19th century that the real power of the 2-state binary system for digital processing was unlocked. They realized that logical true and false statements could map perfectly to mathematical ones and zeros, a real game changer.
Section 2. Escalating stakes, data transmission, and logic circuits.
All right, let's test your logic for a second. If there are no physical numbers, how does a stream of on and off signals physically travel from one device to another? Like, think about a file downloading to your phone right at this very second. What is actually hitting your device?
Now, in just a second, I'm going to give you the exact examiner clue that changes how you answer this entirely. But first, you need the framework that makes that clue super obvious. If you tune out of this explainer now, you'll totally miss the precise vocabulary examiners demand for data transmission questions. So stick with me, because without this exact phrasing, even if your concept is right, you'll drop marks.
To build that technical vocabulary, we first have to understand that these bits are transmitted physically in 3 distinct ways. First up, as electrical pulses traveling down metal cables. Second, as actual pulses of light shooting down fiber optic cables. And third, as wireless signals, which, if you think about it, are really just electromagnetic waves, like radio and infrared, moving invisibly through the space right around us.
And depending on how your network is set up, these physical signals travel in highly specific directions. You've got to categorize them strictly. There's simplex, meaning one direction only, duplex, which means both directions simultaneously, and then half-duplex. That's both directions, but only one at a time, kind of like a walkie-talkie.
So, when those physical signals finally reach a computer's CPU, they hit what we call logic gates. Specific voltages, say a potential of 3 volts, might represent true, or a binary 1. Meanwhile, 0 volts represents false, or a 0. This exact voltage determines the gate's switch setting and dictates the resulting binary electrical output. It is literal, physical cause and effect happening millions of times a second.
Section 3. The mark scheme's secret. Upgrading your answer.
To get those top marks, you absolutely must use this exact 4-step flow. First, you state the technical concept clearly. Second, apply it directly to the specific data or scenario they give you.
Third, provide the scientific or technical reasoning. And fourth, wrap the whole thing up in precise examiner wording. Seriously, do not deviate from this structure. Let's do a quick pause and predict. Ask yourself exactly why a Cambridge examiner is going to look at this generic answer and give it 0 marks. The computer sends binary data back and forth over a wire. Think about it. What is missing there?
Well, here is the secret examiner clue. You must respond precisely to the command word, words like explain or describe, and you have to apply it using the scenario-specific nouns. You need exact technical terms. Completely avoid wishy-washy generic descriptions like back and forth or over a wire.
Look at the difference in the top band upgrade. By specifically identifying duplex transmission instead of just saying back and forth, and calling out electrical pulses over metal cables instead of a generic wire, you perfectly describe the binary states. You are basically forcing the examiner to give you full marks. It's all about precision.
Section 4. The final challenge. Before we wrap this up, always remember this golden rule of the mark scheme. 1 mark normally requires 1 distinct technical point. Never ever repeat the same idea twice in your answer using different words. If you're staring at a 3-mark question, you need 3 distinct technical facts drawn right from the framework we just covered.
Lock this ultimate revision summary into your memory right now. It perfectly connects the physical reality of binary, those 2 electrical states, to the data transmission methods, and finally, to how logic gates use voltage for 1 and 0 decisions. This right here is your ultimate cheat sheet for Paper 1 hardware questions. Okay, so we've successfully debugged your hardware exam strategy. But all of this theory creates an entirely new problem when you sit down for Paper 2. Knowing how hardware flips switches is one thing, right? But how do we harness that raw binary logic to actually write complex, high-level programs? By the way, if this framework is helping you decode the exam, make sure you're subscribed to Ace the Exams at acetheexams_IGCSE so you don't miss our next big strategy breakdown. Because understanding binary is absolutely useless if you can't trace its logic through a high-level program. Before you move on, ask yourself, if every incredibly complex video game and AI is built on nothing but simple on and off electrical switches, how complex do those exam trace tables really get? Well, it's time to find out. Jump into our next explainer on algorithms right now, and let's go master Paper 2.